I welcome you all for this lecture series on deep learning. In this lecture, we will briefly discuss about what is hyperparameters in machine learning. In that, what is the manual hyperparameters and what is automatic hyperparameter tuning, why it is necessary. These things we are going to discuss in this lecture. Before going into this hyperparameters, let me tell you why the hyperparameters are necessary to learn. The topic of hyperparameter is important in machine learning. Hyperparameters are the external configuration settings of machine learning model that control how model learns from data. They play an important role in determining training efficiency, model accuracy, and generalization ability. Understanding hyperparameters are essential because even a powerful algorithm can perform poorly if its hyperparameters are not chosen properly. There are two types of hyperparameters are there. Manual versus automatic hyperparameter tuning is are there. There are two main ways to select hyperparameters, the manual tuning and automatic tuning. Manual tuning relies on human induction and repeated experimentation, while automatic tuning uses algorithms to search for optimal settings. Comparing these approaches helps us understand their advantages, limitations, and appropriate use cases in machine learning workflows. We'll see one by one. First, we'll see introduction to hyperparameters. Models learn patterns using parameters such as weights and biases. In machine learning, everyone knows it all. In machine learning and deep learning, models adjust internal values like weights and biases during training to minimize prediction error. These parameters are learned automatically from the data and represent the knowledge the model acquires about relationship between inputs and outputs. Some settings are not learned from data. That means, apart from learned parameters, there are certain predefined settings that must be specified before training begins. These settings determine how the learning algorithm behaves and cannot be optimized directly through gradient updates or training iterations. These settings are called, we are calling it as the hyperparameters. The such predefined configuration values are known as hyperparameters. They define the structure of the model and control aspects of training process, such as how fast the model learns or how complex it becomes. And hyperparameters control the learning process and influence the performances. That means hyperparameters strongly affect convergence speed, model stability, prediction accuracy, and generalization ability. Proper selection of hyperparameters can dramatically improve model results, while poor choices can prevent the model from learning effectively. Next, everyone should know about what are hyperparameters. Hyperparameters are configuration values set before training begins. Hyperparameters must be chosen before model training starts because they define the learning environment and algorithm behavior. Once training begins, they remain fixed unless the model is retrained. They guide the training process and affect model behavior. These values influence how the algorithm explores data patterns, how complex decision boundary becomes, and how sensitive model is to noise or variations in data. And they are not updated during learning. That means, unlike weights and biases, hyperparameters are not adjusted automatically during a training. Instead, what they'll do is they must be selected manually or through optimization technique before training runs. Next, choosing the correct hyperparameters prevents the overfitting and underfitting. Selecting appropriate hyperparameters ensures the model neither memorizes the training data nor oversimplifies the relationship. This we can call it as overfitting and underfitting. Proper tuning helps achieve balanced learning and strong generalization to unseen data. Next, examples of the hyperparameters are learning rate in neural network. The learning rate, what it will do, the learning rate determines how large the update step is during gradient descent. A very high learning rate may cause unstable training. Very large learning rate, we are usually specifying it as the term eta. A very large update, that is a large very high learning rate may cause unstable training, while a very small one can slow down convergence significantly. Next, number of hidden layers. Number of hidden layers defines the depth of neural network. More layers increase model capacity but also raises the risk of overfitting and computational complexity. Next, batch size. Batch size, everyone knows it of. This we have discussed in our previous lectures also. What do you mean by batch size? What do you mean by the number of hidden layers? Everything we have discussed it. So while you're choosing this batch size determines how many training samples are processed before updating model weights. Small batch sizes, what it will do, improves the generalization, but may slow training. This is what we have seen it in the previous lectures. And while large batches speed up the computations, but may reduce the learning stability. Next, number of epochs. Epochs represent how many times the model passes through the entire training data set. Too few epochs may cause underfitting, while too many can lead overfitting. Next, regularization strength. Regularization hyperparameters control how strongly the model penalizes complexity. They help prevent overfitting by restricting extreme weight values. Next, number of trees in random forest. The hyperparameter controls how many decision trees are built in the ensemble. More trees usually improve accuracy but increase training time and memory usage. Next, the value of k in k nearest neighbor in knn means k nearest neighbor. The value of k determines what? How many neighbors influence prediction. A small k may make the model sensitive to noise, while large k may over smooth the predictions. So these are all the examples of hyperparameters. Next, why hyperparameters are important? They control training speed and convergence. Hyperparameters like learning rate and batch size determine how quickly the model reaches optimal performance. Poor choices can make training extremely slow or unstable, and they affect model accuracy and generalization. Hyperparameters directly influence how well the model fits training data and how well it performs on unseen data. Proper tuning leads to improved predictive power and reliability. And slow learning rate. Slow learning means incorrect hyperparameters can cause training updates to be too small, resulting in slow progress toward optimal solutions. Next, overfitting. What do you mean by overfitting? If the hyperparameters allow excessive model complexity, the model may memorize training data rather than learn general pattern. Underfitting means if hyperparameters overly restrict the model, it may fail to capture meaningful relationship in the data. Next, unstable training. Unstable training means what? Improper settings can lead to oscillations in loss values, divergence in gradient updates, or inconsistent predictions during training. Next, types of hyperparameter tuning. There are two types are there, two main approaches are there. Hyperparameter tuning methods are, that is manually hyperparameter tuning, automatic. And hyperparameter tuning methods are generally divided into two broad approaches, manual tuning and automatic tuning. Both aim to find the best configuration values that maximize model performance, but they differ in how they search for these values are performed. First, manual hyperparameter tuning. Manual tuning involves selecting hyperparameter values based on human understanding induction, and repeated experimentation. The researchers adjust parameters step by step and evaluates performance after each change. In automatic hyperparameter tuning, it uses algorithmic search strategies to explore multiple combinations of hyperparameters. This approach reduces the human effort and often finds better solutions, especially in complex models. Next, manual hyperparameter tuning. We'll see the introduction about that. Manual hyperparameter tuning uses the experience, induction, or trial and error methods. In manual tuning, the practical practitioner relies on past experience, theoretical understanding, or experimental testing to decide which hyperparameter values to try. This method is simple but may not always guarantee optimal results. Next, researchers adjust values and checks performance repeatedly. The process involves repeatedly training the model with the different hyperparameter values and observing how performance changes. Based on these results, further adjustments are made until acceptable performance are reached. And here this is the traditional method used in early machine learning developments. Before automated search techniques became common, most machine learning models were tuned manually. That is, even today, manual tuning is still useful for small data sets and simple models. And how manual tuning works? Choose the initial hyperparameter values. The process begins by selecting reasonable starting values, often based on theory, prior studies, or common defaults. Train the model. The model is trained using the selected hyperparameters, so its learning behavior can be observed. Next, we have to evaluate the performance. After training, performance metrics such as accuracy, loss, or errors are analyzed to determine whether the chosen values are suitable. Next, we have to modify values based on the results. If the results are unsatisfactory, the hyperparameters are adjusted manually to try improving performance. Next, we have to repeat until satisfactory performance is uh, achieved. So this we have to keeps on doing this process until we get the perfect output. Okay. So this process continues iteratively until the researchers believes the model performance is acceptable or improvements stop appearing. Next, advantages of manual tunings are easy to understand. Manual tuning is conceptually simple because it involves directly changing values and observing outcomes, making it easy for beginners to grasp. No special tools are required. Unlike automated tuning methods, manual tuning does not require additional optimization software or complex frameworks. And the next works well for small models or data sets. When models are simple and the training time is short, manual tuning can quickly produce good results without the overhead of automated search. And it gives the intuitive understanding of model behavior. Since the researchers observes how each parameter change affects results, manual tuning helps build strong conceptual understanding of the model. Even though it has got advantages, it to have some disadvantages also. Time consuming means manual tuning often requires many runs, which can be slow or inefficient, especially for deep learning. It requires expert knowledge. Effective manual tuning depends on the practitioner's understanding of algorithms and parameter effects, which beginners may lack and may miss the optimal parameter combinations. Since humans explore only a limited set of values, manual tuning may fail to discover the best possible hyperparameter configuration, not suitable for complex deep learning models. Modern deep learning systems often have many hyperparameters, making manual tuning impractical and inefficient. Next, we'll go for the automatic hyperparameter tuning. Just we'll see the introduction. Automatic tuning uses the algorithms to search for best hyperparameters. Instead of relying on human decisions, automatic tuning methods systematically explore combinations of values using optimization algorithms. It reduces the human effort. Once the search space and evaluation methods are defined, the tuning process runs automatically with minimal human involvement, and it is widely used in modern ML, that is machine learning and deep learning systems. Due to increasing model complexity and computational resources, automatic tuning has become standard practice in industrial and research applications. And common automatic tuning methods are grid search. Grid search means a grid search tests all possible combinations of hyperparameters values from predefined defined list, ensuring a thorough but computationally expensive exploration. Random search means random search samples hyperparameter combinations randomly, often finding good results faster than grid search because it explores a wide variety of values. Next, Bayesian optimization. It builds a probabilistic model of performance and intelligently choosing promising hyperparameters, making search more efficient. Next, genetic algorithms. These algorithms simulate evolutionary process by selecting, combining, and mutating parameter sets to gradually improve performance. Next, AutoML systems we are using it. This AutoML frameworks automatically handle model selection, feature engineering, and hyperparameter tuning, providing strong baseline solutions with minimal manual efforts. How automatic tuning works. Next, we'll see. Defining hyperparameter search space. The process begins by specifying ranges or possible values for each hyperparameter that algorithms will explore. Next, we have to select the optimization method. Tuning algorithms such as grid search, random search, or Bayesian optimization have to be chosen to guide the search process. And we have to train the multiple model with the different values. The system the trains may model using different hyperparameter combination to test their performance, and it evaluates the performances using validation data. Each trained model is assessed on validation data to ensure that performance reflects generalization ability, and it chooses best performing configuration. Finally, the hyperparameter set that produces the best validation performance is selected for the final model. Advantages of automatic tuning. It saves the time and effort. Automatic tuning, all we know that eliminates much of manual experimentation process, allowing researchers to focus on model design and interpretation. Next, it finds better parameter combinations because it explores many possibilities systematically. Automatic tuning often discovers configurations that humans might overlook, and it works well for complex models. Deep learning models with many hyperparameters benefit greatly from automated search methods. Everyone knows it of. It reduces the human bias. Automated methods rely on objective search strategies rather than personal intuition, leading to more reliable optimization. Even though it has got advantages, it too has some disadvantages. It is computationally expensive. Automatic tuning often requires training dozens or hundreds of models, consuming significant computational resources. It requires more progressive power. Large search space and deep models demand high performance hardware such as GPUs or distributed system. It may take long time for large searches. If the parameter ranges are wide, tuning may take hours or even days to complete, and it needs proper validation strategy. Incorrect validation methods can lead to overfitting to validation data and reducing real world performances. Next, the comparison between manual and automatic tuning effort. The first feature is effort. Here, that is high versus low. Manual tuning requires continuous human involvement, where automatic tuning runs largely on its own configured. The speed, if you are comparing slow versus faster, manual tuning progresses slowly due to sequential experimentation, while the automatic method tests multiple combinations quickly. If you are considering the accuracy, suboptimal, and here it is often better. Manual tuning may settle for acceptable solutions, while automatic tuning often discovers more optimal configuration. Cost, low computation, high computation. Manual tuning needs less computing power, but that is automatic tuning consumes more computational resources. This is best for small problems, and this is best for complex ML and DL model. Manual tuning suits for simple problems, whereas automatic tuning is ideal for large data sets and deep learning systems. So, role in model evaluation. Tuning directly impacts performance. Hyperparameter choices strongly affect how well a model learns pattern and generalizes new data. It improves accuracy and stability and generalization. Proper tuning ensures the model coverage smoothly, avoids overfitting, and performs reliably on unseen samples, and helps us select best model before deployment. Tuning allows comparisons of multiple configurations so that most effective versions can be chosen for production use. Yeah, it is essential for essential step in optimization pipeline. Hyperparameter tuning is now considered a core part of the machine learning workflow, not an optimal step. Next, what are all the key takeaways from this lesson is lecture is hyperparameters control how model learn. They determine the structure, training, speed, and complexity of model, making them crucial for performance. Manual tuning relies on experimentation, experience, and trial and error. It depends on human judgment and repeated testing, making it suitable for mainly for small and simple problem. Automatic tuning uses search algorithms. Model methods systematically explore parameter combinations to find optimal setting efficiency. Both models are useful depending on the problem complexity. The choices between manual and automatic tuning depends on what? Problem size, resources, and required accuracy. And the proper tuning is important for achieving high performance model, no matter how advanced the algorithm is. Good hyperparameter selection is essential for achieving reliable and accurate machine learning models. Hope everyone understood about this topic, automatic and the manual hyperparameter tuning. The remaining things we'll discuss in detail in the next lecture. Thank you.